Apparent gravity. The apparent gravitational force per unit mass is that which arises from the geopotential. And we know that the geopotential has two components, that due to the ordinary Newtonian gravity and that due to the centrifugal force. So the Fa, the apparent gravitational force per unit mass, is equal to Fg, the Newtonian gravitational force, plus Fc, the force due to the centrifugal force on M. And that's equal to the sum of the two geopotentials, phi g, or the gradients in them rather, minus grad phi g minus grad phi c, which is equal to minus grad of capital Phi. That's shown schematically in the figure below. So for a sphere, Newtonian gravity would point along the local normal, and that would be inward towards the centre. The centrifugal force points outwards from the axis of rotation, and so the apparent gravity is now no longer along the local normal for a sphere. But as noted in other lectures, this apparent gravity will deform the sphere into an ellipsoid. And so what that means is that gravity, the apparent gravity, will continue to act in along the local normal. It's just the local normal no longer represents a sphere but an ellipsoid. And that's shown here. In meteorology, we'll always use the apparent gravity and not the Newtonian gravity. Up is normal to the geopotential surfaces. It's in the opposite direction to the apparent gravity force, Fa, and in the same direction as the gradient in geopotential. So there's up, and the force due to gravity is down. We can talk about a reference ellipsoid, which is a theoretical reference geopotential surface that best matches the Earth's mean sea level pressure. The reference ellipsoid is smooth and assumes there are no small-scale variations in gravity, which of course we know is not the case because we have mountain ranges and variations in the density of the material underneath us, which is what mining geologists use to find ores, etc. The best reference ellipsoid is called WGS84, and here it is, showing that the radius of the Earth at the equator is larger than it is at the poles. The real Earth, of course, has, as noted, a crinkled surface with topography, valleys and mountains and so on, and density variations. Consequently, there are small local variations in phi g. The geoid is that real geopotential surface that best matches the Earth's MSLP, and the best current geoid model is EGM 96, for those who are interested. And here are deviations of the geoid from the idealized figure of the Earth. The blue shades represent areas below the idealized ellipsoid and the red areas above it.